Okay, so let us now solve for this problem. So this problem is still in reference with ACI 318-14M and NSCP 2015. Okay, so in this particular problem, we would now be designing the shear reinforcement of a 6-meter simple beam that carries an unfactored dead load of 35 kilonewton per meter and a total factored live load of 48 kilonewtons per meter. The columns carrying the beams are square columns of dimension 400 mm, and we would now be considering F prime C equal to 21 megapascal, Fy is equal to 420 megapascal, and Fyt is now equal to 280 megapascal. And take note that the cross section of our beam would now look like this, whereas the breadth of the web, or BW, is equal to 350 mm, and the effective depth is now equal to 425 mm. So we would now be making use here 5 diameter 25 mm rebars, which does not have any use in this video. Okay, so anyway, so in this video, we would now be solving for it via simplified method first. Okay, so the first thing that we will now be doing here is for us to solve for the shear diagram of our section. So shear diagram first. So in order for us to solve for our shear diagram, we must first know what the load is. So for the load, as you can see here, that we have an unfactored dead load of 35 kilonewton per meter and an unfactored live load of 48 kilonewton per meter. So from that, guys, I would now get the load combination of it. And from that, guys, the uniformly distributed load, or the ultimate uniformly distributed load, is now equal to 1.2 dead load plus 1.6 live load, and that is now equal to 1.2 times 3.5, that is the dead load, and plus 1.6 times 48, and that is now the live load. So looking at the calculator to your left, so that is now equal to 1.2 times 35 plus 1.6 times 48, that is now equal to 118.8. So that is now 118.8 kilonewton per meter. Okay, so from that, in order for us to successfully know what the value of our shear here is, so basically this is the reaction. So we should now solve for the support reactions here. So it would now be up to you how you would be solving for the support reactions. It is either you would be getting the summation forces horizontal or get the moment about a particular point. However, since in our video or in our problem here, the problem actually shows us asymmetric loading. So meaning that this reaction here is actually the same as with our reaction here. Kasi maghahati lang naman sila, pantay naman po yung loading. So, again, it would be up to you how you would be solving for it. But in my case, I would just be solving it like this. So, 118.8 times. So, it is stated here that it is actually 6 meters long from center to center. So, from that, I would be multiplying this by 6. So, this is now the resultant. So, the resultant of our load is now 712.8. So, again, it is now 712.8. And since it is symmetrical, both of our reactions here would have their own equal share. So basically, their equal share is just that we would just be dividing the resultant by 2. So I hope that is clear. So this now equal to 356.4. This is also 356.4. Again, this is also 356.4. And this is now negative 356.4. So if you are getting confused here, I think you should first review mechanics of deformable bodies before proceeding. Okay, anyway, so according to our provision before, that if we are now given a particular beam and it checks all of these conditions, so whereas the support reaction introduces compression, loads are applied at or near the top surface of the beam, and no concentrated load occurs between face of support and critical section, we can actually say that the critical section is located at a distance d from the face of support. So going back to our figure here, we are now to assume that, let me just write, our critical section is located at a distance d from the face of support. So meaning that in our design, this is now our critical section, or this is now the critical section. And that is now VU at D. So it would be up to you on how you would be solving for this particular shear force here. Either you would be solving for it via ratio and proportion, or you can just make use of shear equation method. So shear equation method is actually the safest route in solving for your shear, because ratio and proportion is only applicable if and only if you have a linear or a uniformly distributed load. In a situation wherein you would be having, let's say, a triangular load, you cannot make use of ratio and proportion, not in my knowledge. So again, for safe purposes or for safe values, so again, our reaction is 356.4. So again, 356.4. So this is the reaction. And I will be cutting a section at this particular point. So from that, when I have cut the section, it is actually here. So I will now assume that that is now the distance D. So what is now the distance D? So the distance D, that is 425 mm. So the effective depth of my beam is 425 mm. So from that, guys, this is now 425 mm at this particular arrow. So this is 425 mm. And take note, guys, that when we said 6 meter simple beam, it is from the center of this of this beam to this beam. So we must first take into consideration what this dimension is. So this dimension is actually half of the column dimension of 200 mm. So from that, guys, that is now 0.2 meters or half of the column dimension. And from that, guys, again, this is D here. So this is D. And that is 0.425. So meaning, adding 0.2 and 0.425, we now have 0.625 here. So what I would be doing in order for us to know what the shear here is, I would now be getting the summation of forces vertical, and that is now equal to 0. And from that, guys, call this, what are the forces present in our figure here? So we have a positive 356.4 kilonewtons minus what is the resultant of our uniformly distributed load. So minus 118.8 times 0.625 plus VU. So this is now equal to 0, and solving for the value of VU at D, we would be arriving at an answer of, so looking at the calculator to your left, that is now equal to 118.8, or sorry, so 118.8 times 0.625 minus 356.4, or you can actually use shift solve method here. So from that, guys, my answer is now equal to negative 282.15. But take note that this negative value here only indicates that I have assumed the wrong direction here. So just get rid of the sign. We are only particular with the magnitude. So again, VU at D is equal to negative 282.15. Or once again, I would be omitting the negative symbol. So 282.15 kilonewton. So this is now the value that we will be referring to. Okay, so another way in order for you to do that, since in our problem here, we have a uniformly distributed load. So what I would be doing, guys, is that I know for a fact that at this particular portion, or at this particular point, which is at the middle, V there is equal to 0, okay? And at the start, I know there that the V is equal to 356.4. I could actually make use of mode 3.2 in my calculator. So that is mode 3, stat mode, and then 2, A plus BX, in order for me to get a table for a linear table, I should say. And what I would be doing here is that I would be plotting my points. So I know for a fact that in what you are seeing in front of you, that at x is equal to 0, the shear force there is actually 356.4. Okay? And you also know that when shear is equal to 0, So when shear is equal to 0, x is equal to 3. Why 3? Where did this 3 come from? So this is the midspan. So this is 3 meters. So at x is equal to 3 meters, the value of b is now equal to 0. Okay, so now that I have already completed my table here, I would now be pressing ACI. I would be clearing it. And I would now be getting the features of stat mode. So in my calculator cars here, I would now be pressing shift 1 or stat mode. And I would be pressing 5. So 5. And since I want to know what the shear at this particular point is, so I want to know the shear here, I would now, in my calculator, press bar y, or y caret, I should say, 5, which is y caret. But before the y caret, I would be telling the calculator what is the x dimension. So, again, in our situation here, the x value is equal to, so, whatever this distance is. And this is, according to our computation a while ago, this is 0.625. So from that, looking at the calculator once again, I would be typing 0.625 here. And from there, we now have the same answer with our computation earlier, which is 282.15 kilonewtons. So it would now be up to you which method you will be using, but if it would be up to me, I would be choosing this option instead because it is faster. Okay? But take note, guys, that our calculator technique here is not applicable for triangular loadings. This is only applicable for straight or uniformly distributed loads that would result to a straight shear diagram. Okay? Okay, so now that we already have the value of BU at D, so again, we now have the value at, or VU at D, which is the shear at the critical section. Let us now solve for the value of VC. So again, in this video, we would now be making use of the simplified method, and according to the simplified method, VC, let me just erase this. So VC is equal to 0.17 times lambda times square root of f prime c times BWD. Okay, so let us now make use of that equation to our problem here. So from that, guys, substituting all known values, 0.17 times lambda, lambda is just 1, square root of f prime c, so as you can see, f prime c is 21, BW is 350, and D is equal to 45. So that is now equal to 0.17 times 1 times square root of 21 times 350 times 425. So let me just calculate that. So 0.17 times square root of 21. So let me just go back to computer mode here first. So 0.17 times square root of 21 times 350 times 425. So sorry, this should be 0.17, I should say. So my answer here is now equal to 115,881.8829. So take note, guys, that since in our formula here, I have made use of megapascal and I have made use of millimeters and millimeters, the answer here is now in terms of newtons. Okay. So again, it is now in terms of newtons. So if that is VC, again, my first concern is for me to solve for VS first in order for me to solve for the theoretical spacing required. So again, this VC here indicates that this is the strength of the concrete, which is 115.881. 115.881 kilonewtons or 115.881.883 newtons. So let me just solve for phi VC first. So by phi VC, that is just multiplying 0.75 and 115.881. So let me just multiply our answer here by 0.75. So the design strength for the concrete shear or the shear strength of the concrete is equal to 86,991.41 newtons. Okay, so take note of this, guys. PVC or the design strength of concrete is 86,991, but it should be carrying to 82.15. So does that mean that we need to have shear reinforcement? So basically, yes. Because 86 is less than 282. So meaning he needs backup. So by backup, our concrete must have the help of our stirrups. So in order for us to know how much newtons the stirrup should be carrying, so we would be back solving. So again, guys, this is since VU is now greater than PVC, shear reinforcement is required. And in order for us to solve for VS, okay? So it's, in order for us to solve for VS, as you know a while ago, that VU is equal to V VC plus VS. So making use of this equation, substituting all known values, so 282, 150 newtons. This is equal to, what is the value of P? That is 0.75. What is the value of VC? VC is equal to 115,881.883 newtons plus VS. So we do not know the value of VS is. So solving for VS, so I would just be writing them here. So VS is now equal to, so looking at the calculator, so it is either you would now be transposing it, or let us just make use of shift solve here. So 282,150 newtons, that is now equal to 0.75 times 115,881.883 plus alpha x. So from that, shift solving, my answer, so VS is now equal to 260,318.117 newtons. Okay, so that is the theoretical force, or the theoretical shear force that the shear stirrups would be carrying. Okay, so from that, guys, let us now solve for the required spacing in order for us to get a VS like this. Okay, so according to the code, S is equal to AVFYT times D over VS. So substituting all known values, S is equal to AV and AV is equal to, so what is AV here? So since our shear force is towards this direction, meaning that we would be having two legs, okay? So we would be having two legs. So for AV, that is now equal to, so it was not indicated in the problem, so I would just be choosing for a diameter. So I would be choosing for a diameter of 10 millimeters for my shear reinforcement. So with that, guys, the value of AV is now equal to, so since I have two legs, as per emphasized here, 2 times the area of one rebar, which is pi over 4 times 10 squared. And from that, AV is now equal to, looking at the calculator to your left, so that is now equal to, so 2 times pi over 4 times 10 squared. Oops, sorry. So 10 squared. Syntax error. 2 times pi over 4 times 10 squared. So that is now 50 pi. So 50 pi. So from that, guys, S is now equal to 50 pi, which is AV, times FYT. So again, this is the yield strength of the transverse steel, and that is 280 megapascal. So times 280 megapascal times D, and our effective depth is 425. So divided by what the value of VS is. So VS is equal to 260,318.117 newtons. So take note that our answer here must be in terms of newtons in order for us to have consistency in units. So from that, the value of S is now equal to, looking at the calculator to your left, I should say, 50 times, so once again, 50 times pi times 280 times 425 divided by 263,318.117. So our answer here is 71.806 millimeters. So theoretically speaking, this is the required spacing for a shear load of 282.150 newtons. So meaning, guys, in our structural plan, the spacing at the first one, at this region where it is, let's say that this is now D, just for pretend. So let's say that this is D. So meaning that our spacing here must be, I'm sorry, S is equal to 71.806 millimeters. However, if you would now be drawing the details of the plans, this is actually kind of illogical in a way, because if the steelmen would now be installing that rebar or those rebars, I think that they do not have a caliper or a vernier caliper to um, plot 0.806 of a millimeter. So instead, as a safer option, I think it is better if we would just be making use of a value that is below it. So if you're wondering, do we round up or do we round down? So short answer to that is that we should round down, because as you know, the less the spacing is, so imagine nyo na lang, mas oonti yung spaces nila. So the lesser the space is, the stronger it is. So if you would be rounding up, so the spacing would now be farther, meaning that the shear force of the stirrups would now be less. Okay? So the shorter the spacing, the better. So from that, I have rounded this to 70 mm. So short answer, is that our answer already? So not a short answer, but rather a question. Is that our final answer already? We are not yet sure. So let us first check for the maximum spacing. So for the maximum spacing according to NSCP 2015, it is either D over 2 or 600 if let's say your VS is now less than or equal to 0.33 square root of F prime CBWD, or D over 4 or 300 if let's say the VS is greater than 0.33 square root of F prime CBWD. So, sir, why didn't we use this? Because this provisions here is only for pre-stressed beams, and according to our problem, we are solving for a non-pre-stressed beam. Okay, so with that, guys, let us solve for this limit first in order for us to check which of the following we would be using. So again, let us solve for 0.33 square root of F prime C BWD, and substituting all known values, that is now 0.33 times square root of 21 times 350 times 425. So looking at the calculator to your left, 0.33 times square root of 21 times 350 times 425. Our answer here is 224,947.1844 newtons, and that is now this answer here. Okay, so take note that since VS, so again, our VS earlier is 260.318 or 263.18.117. Since it is greater than our limit of 224,947, meaning that we will now be making use of either this value or this value. So let us solve for the both of them. So again, we will now be making use of this section. So for the first one, so for D over 4, that is now equal to, so the depth of our beam is 425. Wait, I think, I'm not sure. So was that 425? So yes, it is 425 indeed. So again, that is 425 mm divided by 4. So looking at the calculator to your left, so that is now equal to 425 over 4. So 106.25. So 106.25 millimeters. Okay. So what about for 300? So 300. Okay, so which one do you think would govern? So the one governing here is of course the smaller value. So as you can see here, the lesser of. Okay, so 106.25 mm. And since once again, it is rather weird if you would be putting 106.25 mm in the structural plans. Rather, we would now be making use of 100 mm. Okay, so in our answer here, or previously, our answer was 70 mm. So since the maximum spacing that we used is 100 mm. So our conclusion here. So conclusion, since 70 mm is less than 100 mm, 70 mm would govern. Okay? So since it is less than 100, but in a situation we're in, let's say, for example, that the S required was, let's say, 120, then your S max is 100, you would now be making use of 100. So whichever is lower between these two. Okay? Okay, so from that, guys, again, let's say that this is the whole of our beam. Let me just bring back my laser pointer. So suppose that this is now the entirety of my beam. And according to our plotting a while ago, this is, let's say, at a distance d of 425 mm. And the VU that we have solved for there is 282.150 newtons. And as we know, guys, that from the first one, or from the face of the footing up until this region here, the spacing of the stirrups must be 70 millimeters. Okay? But what about for the rest of the beam? Would we use 70 mm throughout? You could actually do that, but of course, it would be rather uneconomical. So again, let me just repeat my statement. You can use the spacing of 70 mm for the entirety of the beam. It would be safe, but it would be inefficient. It would be uneconomical. Because as you can see here, guys, that for our shear, as it goes to the midspan, it actually decreases up until 0 here. So, making use of 70 mm spacing at this particular region, once again, is uneconomical because we do not really need that much spacing. So, okay, so with that being said, I could say that since the shear force here is 0, or the shear stress here is 0, we can see that theoretically speaking, that the shear stirrups here, or shear stirrups here, is not actually required. Correct? Okay, so yes, it is correct. We do not really need shear stirrups here because the concrete can actually carry the shear here, which is 0, of course. So let me just divide this, or the entirety of my beam, into sections. So I would be getting the location where, let's say, VU is equal to PVC. So let me just retype that for a moment. So again, for in this, so this is now equal to VU. Oops, sorry. So that is not VY. So VU is equal to PVC. So from there, VU is equal to PVC. Let me just rearrange that. So VU is equal to PVC. So again, the PVC that we have solved for earlier was 86.991 kilonewtons, or 86,991.41. So if VU is equal to 86,991.41, it is located here at this region. And I will be dividing this region further. So half of it, so 86,911.41 divided by 2, that is 43455.7. So what is now the use of these regions, or these values? Okay, so according to the code, and according to practices, at this region here, whereas VU is equal to PVC, okay? If VU is equal to PVC, guys, we can say that VS here is actually equal to 0. Why is that the case? So, suppose that VU is equal to PVC, whereas from our equation, VU is equal to phi VC plus VS. And if VU is equal to PVC, so VU is now equal to PVC plus PVS. And substituting known values, 86,911.41 is equal to 96,911.41 plus PVS. Okay? So, solving for the value of PVS, you would now be arriving at a VS is equal to 0. So, meaning at this particular region, going towards the right. Okay? So take note that from this region to the right, Vs is now equal to 0. With that being said, theoretically speaking, we do not actually need stirrups here. We do not need stirrups there since concrete can already carry them. So kaya na po sila ng concrete lang according to our equation here. So again, if Vu is equal to PVC, meaning Vs is equal to 0 from this equation. And if Vs is equal to 0, meaning that if you would be solving for, if you would be solving for, let's say, the spacing using this equation and substitute Vs equal to 0, you would be arriving at an answer of infinity. So meaning infinity spacing, meaning spacing or steel rebars is actually not required there. Okay, so proceeding. Let me now, let me just rephrase. Again, theoretically speaking, we do not need shear reinforcements here. However, according to the practice and according to the code itself, we can actually provide SMAX here. Okay? So, let me just erase this part here. What I will be doing is that I will be providing SMAX. Okay, so in here, I would now be providing another SMAX, or you can just leave that alone since it is, since theoretically speaking, no stirrups is actually required there. So the next thing that I will be doing is that I will be locating these points here. So how can I be locating that point? So it would be up to you. You can once again make use of the shear equation. So let's suppose that you would be making use of this shear equation. Then substitute the value of Vu. Then you would be solving for the value of the distance. Or this time, I would now once again make use of, spoiler. So I would now be making use of my calculator technique or the calculator itself using stat mode. So mode 3, 2. So again, I know that at this particular point that is, well, actually I forgot. What was the support again? So that is 356.4. So at this portion, that is now 356.4. So by my calculator, at x is equal to 0, y is equal to 356.4, and at x is equal to 3, I know that y is equal to 0. So again, at x is equal to 3, y is equal to 0. Okay, so from that, I would now be clearing this once again. And let's say that I want to solve for my value of x here. I will be naming this as x1 for suppose. So x1 is now equal to, so what is now the value of x if y is equal to 86911.41? So from that, I will now be typing 86. So 86.99141. So take note that I have made use of 86.99141, meaning that this is in terms of kilonewtons. Okay. So shift 1, 5, and I will now be pressing the x caret. Okay. So why x caret? Because I want to know the value of x. Okay, so solving or pressing 4 there, x caret. So this value is equal to 2.2677 or 2.2688. 268, I should say. So that is 2.268 up until that portion. So next up, for PVC or 0.5 PVC, that is now equal to, so looking at the calculator, where's my calculator? So where's my calculator? So I would now be typing half of it here. So for a shear force of 43.4557 kilonewtons of shear, what is now the value of x? So the value of x is now equal to 2.263. Okay? So that is now 2.263 2.634, I should say. Where did I get 2.634? 2.634. So that is now 2.634. Okay. So what's next? So let us now solve for S max here. But take note, guys, that for the value of S max, we could actually extend it to the left. So what do I mean here? The truth is, theoretically speaking, from this portion, to the right, we could provide S max. Okay? However, from this point to this point, actually we could still extend the region for S max to the left. Okay, so what do I mean here? Diba ang sabi ko nga po, pwede pa po natin siyang i-extend to the left. But by how much? So, for the value of S max, so from this table, so as you can see here that all of these values have values. So, it is not zero. Okay? So, from that, since it has values po, we could actually solve for their strength of Vs. Okay? So, with that, guys, it is not really zero, or Vs is not really zero if you would now be making use of S max. So, from that, guys, from the value of S max, let us solve for what is its true strength. Okay, so what is now the value of S max here? So if you're thinking that we would still be making use of this value of 100 mm, then you are actually mistaken. Apologies. Because again, in this particular region, guys, we have stated that Vs is now equal to 0. So dito nga po sa part na to, Vs daw is equal to 0. Again, in this table, ito pong 100 mm na yan, that is only true for this region. So at this region, Vs max is equal to 100 because, of course, this was our basis for the value of Vu. Okay? So again, in order for us to know what the limit of S max is, let us just choose. Or let us just back solve, I should say. Okay, so which of this will we be using? This one or this one? Again, in our region, Vs is equal to 0. So this is at PVC, or Vu is equal to PVC. So at Vu is equal to PVC, Vs is equal to 0. And since Vs is equal to 0, it actually falls in this category. And from that, we will either choose D over 2 or 600. So for D over 2, so this is now equal to 425 over 2. So from that po, looking at the calculator once again, so 425 over 2, that is equal to 212.5. So as you can see, that 212.5 is actually less than 600. Thus, let us make use of this value, or rather, let us round this down to 200 mm. So from that, guys, I will now be choosing for an S max equal to 200 mm. Okay? So again, 200 mm. Okay, so next up, let us solve for the strength of a 200 mm spacing. So as you have heard before, or as you can remember, Vs is actually equal to AV FYT D divided by S, or S is equal to AV FYT D over Vs. So it will be up to you which one will you memorize. Just take note that both of them came from the same equation. Okay? So proceeding, substituting known values, Vs is now equal to, so AV, as per our previous computation, AV is equal to 50 pi. So once again, AV is equal to 50 pi. So 50 pi times FYT of 280 times D of 425 divided by S, and the S that we are solving for is 200 mm. So this is now equal to, looking at the calculator, 50 times pi times 280, 280, I should say, times 425 divided by 200. So our answer here is 93462.38 newtons. But take note that we are actually solving for VU and not VS. So VU, if VS is equal to 93462, so VU is now equal to, so again, this is now equal to phi VC plus VS. And from that, VU is now equal to phi of 0.75 times, what is VC? So I actually forgot. What is the value of our VC? So the value for our VC is 115,881.883. So once again, that is, okay, I forgot again. So 115, let me just type in my calculator in order for me not to forget. So 115,881.883. Okay. So from that is now equal to 115,881.883. So 115,881.883 plus VS, that is 93,462.38 newtons. Okay, so with that, guys, the answer is actually equal to 157,008.198. So let me wrap up this slide right here. So again, in this region, towards the right, we will be providing an S-max, even though that VS there is actually equal to 0. Though theoretically speaking, hindi naman po talaga kailangan ng stirrups dito, pero magpo-provide pa rin po tayo ng S-max. And hindi naman po talaga 0 yung S-max natin. So, for S-max, VS is not really 0. And what we did here was that we have solved for the value of VS if S here is now equal to S-max. And we have found out that the value for VS is 93 kilonewtons. And from that, we have solved for a value of VU, which is 157,008.198. So, there. So, proceeding, at VU is equal to 157,008.198, we can solve for a distance of 1.678. Okay? So, meaning, at this region here, let me just highlight it. So, at this, let me just change the color. So, at this region here, guys, so from this point to, let's say, this point, okay, we would be providing a spacing of S-max. Okay? So, again, we would be providing a spacing of S-max here, which is 200 mm. What about for this portion here at the left? So we know for a fact that from this point, from the face of the support up until VU is equal to VU at D, we would be providing a spacing of 70 mm. But what about for this region here at the middle part? So for accuracy purposes, you could actually solve for whatever this shear is. I mean, for whatever the shear here at the regions are, then you can theoretically solve for their individual spacing. So, ibig ko po sabihin, kung gusto niyo pong malaman kung ano po yung mga spacing na nandito, kunin niyo po, yung kunwari, nandyan sa point na yan, kunin mo yung shear niya, tapos solve mo po ulit yung spacing, then that is now the spacing that you will be doing. But for the sake of the discussion, guys, I will be providing 70 mm at this region. So, from this region up until, let me just change the color. So, once again, from this region up until this region. So, up until the support, I will be providing an S equal to 70 mm. But this is kind of an over-design already. So, yun, safe po siya pero hindi naman po siya gaanong efficient. Kasi hindi naman po talaga kailangan ng 70 mm sa part na to eh. So again, just for the sake of discussion, I will be extending 70 mm up until this portion. So actually guys, plenty of engineers do that and even in board exams, minsan ganito po yung approach natin doon. However, multiple choice naman po doon and during board exams, what you would be asked there is the theoretical spacing, the value of PS, and etc. Okay. So, let us put our focus here first in SMAX. Okay? So let us put our focus here first at SMAX. So we also have a provision for AV mean. Okay? So we have a provision for AV mean. So ang gawin po natin, let us check if this setup here, so kung itong setup na to, pasok po siya sa AV mean. So according to our code, we have a code here. So let me just copy and paste the code provision at that particular slide. So, saan ba yan? So here. Okay? So AV mean over S, according to this table, for non-pre-stressed beams, it is the greater of the two. Okay? So AV mean over S, this is equal to 0.062 times square root of F prime C, and our F prime C is 21. Was it? So check ko nga muna if 21 po talaga. So yes, 21 times BW of 350 divided by 280. So the answer here is equal to, so looking at the calculator once again, so 0.062 times the square root of 21 times 350 divided by 280. Answer here is 0.355. Okay, so this is millimeters squared per millimeter. So this is AV mean over S. So this is also equal to, so what about for the second one here? So once again, this is 0.355 millimeter cube per millimeter. Okay, so next up, so for 0.35 times BW times FYT, this now equal to, so BW is 350 and FYT is 280. So looking at the calculator once again, so 0.35 times 350 divided by 280, our answer here is 0.4375. So we would now be choosing this value here. Yan na po yung pipiliin po natin. So from that, guys, this is 0.4375 millimeter squared per millimeter. Okay, so this is now our AV mean. Okay, so AV mean over S. So let me just add another slide. So again, for our confirmed AV mean over S, that is now equal to 0.4375 millimeter squared over a millimeter. So from that, guys, if the S max that we have used is equal to 200 mm, so it means that that is actually this particular section. Saan na yun? So sa section po na to, S max is equal to 200 mm. Just substitute 200 mm to this value. So from that, AV mean is now equal to, so cross multiplying, that is now 200 times 0.4375 millimeter squared per millimeter. So from that, this is now equal to 200 times 0.4375. So our answer here is equal to 87.5 millimeter squared. So meaning that this is AV minimum. So this is now AV minimum. Okay, so if that is the limit, what is the AV actual? So from the previous computation, we have solved for AV equal to 50 pi, or that is equal to, so this came from the equation 2 legs times pi over 4 times 10 squared. So dyan po nanggaling itong 50 pi na yan. So 50 pi, according to our calculator, so 50 times pi, this is equal to 157. So from that, guys, AV mean is now less than AV. So meaning, guys, our computation is adequate, meaning that the value for our AV is adequate. So goods po siya. Okay, so theoretically guys, from this, at this portion, looking at this provision po. So where was that provision? AV mean shall be provided in all regions where VU is greater than 0.5 PVC. So meaning guys, from this region, so from 0.5 PVC to the left, dapat daw po maging adequate yung AV minimum. And since, yun nga po, sa computation po natin dito, goods siya, edi goods na po siya. So sir, do we need to solve for the value for AV mean if S max or if the value of S is equal to 70? So pwede pa rin po. However guys, as you can see here, this is actually more critical. Because if you would be substituting 70 here, the value here would be less. Kasi 70 times 0.4375, mas maliit siya eh. And you would still be comparing it with the same value for AV. So kahit isang beses mo lang po i-confirm, yung sa S-max lang po, pag goods na po siya, it is already good for the entirety of the beam. Okay? So, next up, what do we provide here? So actually, theoretically, hindi naman na po kailangan, pero for your own safety or for the safety of your design, you could actually provide any spacing here. So, again, any spacing. So, maybe I will be providing a spacing of 300 mm. Okay. So, next up guys, in your summary, kailangan nyo pong sabihin kung ilang piraso po sila when you are designing, let's say, a structural plan. Okay? So, according to the code guys, this is a code provision here. For the first one, or for the first spacing, it is actually required that at least one should be 50 mm. So meaning guys, if this is the face of the concrete, the first stirrup must be located 50 mm from that point. Okay? And from that point forward, you would now be providing 70 mm spacing. Okay. So how can we solve for the number of stirrups towards that direction? Just get this particular, this distance, I should say. So, kunin nyo lang naman po yung distance po na ito. From this point to this point. Then, divide it by 70 mm. So, from that distance, so that distance is equal to, so if this is 1.678, so as you can see here, this is 1.678. So, saan po nanggaling yan? Dito po sa, sa shear na ito, pwede po kayo mag-mode 3 to alert or ratio in proportion. Okay? So, from 1.678 minus, once again, this is 200 mm or 0.2. So, from that, looking at the calculator, so, nasan ba? So, 1.678 minus 200 mm. But, as you can remember, gumamit po tayo ng iisang 50 mm. So, we have used 150 mm already. So, from that, guys, let us subtract this by 50 mm further or 0.05. So, this is now the distance po, which is 1.428. And we would be dividing this by 70 mm. In order for us to know how many 70 mm are there. Oh, sorry. This is in terms of meters, so equals. Divide this by 70 mm in terms of meters once again. So, that is 0.07, I should say. So, from that, guys, this is now 20.4. Okay, so do we round up or do we round down? So, if you would be asking me, I would rather say that we would be rounding to the nearest number. Because if we would be rounding up, sa totoo lang, kapag mag-round up po kayo, guys, lalagpas na po siya dito, which is over-design already. If you would be rounding down, it would now go back here. Diba? So, it would be going back here. So, sir, isn't that unsafe? Actually, it is safe because at this portion, hindi naman po talaga kailangan ng 70 mm. Diba? So, again guys, since we have solved for a value of 20.4, I will be rounding that down into 20 mm. So, looking at our summary here, I would be typing, so looking at down, 20 mm. So, 20 mm. So, with that guys, next up, at this region, alamin ko po kung ilang piraso pong rebars yan or stirrups. So, as you can see here, this is 0.956. So, 0.956 divided by, so, ano po yung spacing niya? That is 200, which is 0.2. Okay. So, that is 4.78. So, if you would be rounding up, lalagpas po siya dito. If you would be rounding down, magkukulang po siya. Again, it would be up to you. So, I would say round down na lang para hanggang dito lang siya since theoretically speaking at this region naman po, di ba? Di naman po kailangan ng stirrups. However, I would say na siguro pwede naman na po tayong mag-round to the nearest number, which is 5. And from that, guys, maglalagay na po ako dito ng 5. Para lalagpas lang po siya dito. Pero safe pa rin naman po siya, di ba? So again, with that, I would say this is 5. Then what about for this one? Rest at. So for the rest, so ang sabi ko lang po kanina, 300 mm, but you can actually provide 600 mm here, whichever you like, but I would rather say, na theoretically speaking, or by experience, I would say na pwede naman 300 mm until center line yan. Okay. So ito pong method na to is rather, once again, not really much economical, pero pwede na po siya. If you really want to have an economical section, pwede po kayo mag-detailed. Ang gawin nyo po for every segment, isolve nyo po yung theoretical spacing and the maximum spacing. So with that, guys, pwede po actually kayong mag-excel, or you can use you can draw a table instead. So for the table, let me just draw a sample table here for a moment, guys. Okay, so once again, if you want accuracy, pwede naman po kayo mag-table in this manner, whereas let's say you have a particular location, so at a distance from, let's say, the support. So ito po kasi sinolve natin, which is the first one only. So at a distance 0.625, meaning that this is VU at D. We solve for a VC of 1158881.83. Then from that, we have solved for a VS, which is 260. Then from this one, we have solved for the S required. Then the S max. Then we have chosen what the value of 70 mm is. Then instead of you extending, just like what we did earlier, na nag-extend lang po tayo hanggang dito sa portion po na yan. So again, as you can see, we just have extended it here. Pwede naman pong ibahin nyo. So you can, let's say at a distance, 0.75. Solve for the VU, solve for the VS, S required, S max, S govern. Then let's say at 1 meter, solve for VU, VS, S required, S max, govern, and etc. So yun po mas accurate. List nyo po sila one by one. Okay? So again, for today's lecture, we would be making use of this as our answer po. So there.